Test, 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 1, 2, 3, test. Test. Test.
Okay. Hello, everyone. Is everyone seated? So, okay, welcome to our 45th already meetup of women in machine learning and data science. I'm very happy to see all of you here. It's actually my first time on stage. I used to be on your seat, and I'm very, very happy to be part of the organization team. Thank you. Especially for such a great panel. So today we're going to have 5 wonderful speakers, and I'm really, really excited to hear you speaking. So first, who is here for the first time? Okay. Okay, that's very good. Who has already been here 2 or twice or more? Okay, it's like 50-50. Well, then for those who don't know, Women in Machine Learning and Data Science is a global organization that was created in the US, if I don't say it. Okay, and it's an organization that is free and supporting women from all the sectors. Either it's their field of study, field of interest, or if they're working in this field, they can come and find a very, very friendly community that we have here. And we are present in all over the world with over, I think now 70,000 members. And here is the Paris chapter. We just turned from the 3rd to the 2nd largest community in women in machine learning data science. And we have over 5,000 people on Meetup. So if you're not on Meetup already, please come. And we are 5 members. I didn't change the photo. All of us almost are here. Just Chloe is not here with us, but you can find Nathalie, Marie, Caroline, Juliette. I think she's still there, and me. And what do we have? And what we do, we organize events like this one where everyone is welcome. It's just that our speakers are female, and everyone can come regardless of gender. We have very more prominent speakers, but also we like to have speakers who speak for the first time on stage so they can share their work for more people than their team in their company or research. We also have other events that are online. It's BBL for Brown Bag Lunch, where it's, okay, there's Victoire there who organizes it. And if you like research papers, you can come. We just discuss one paper, and we have a researcher or someone that is interested in one paper that will come and explain things to us. You can also find ideas of papers every Friday on our Twitter X and now LinkedIn account. And we all also can organize joint events. Today it's Women in Big Data Content Square, and Sharon will present it later. Just a word, it's very, very important to us to have this community, because today we have still a long, long road to go. We can see in recent news that we still have too many people that just do all male organized events organized, and we are really active on social media to just make things I mean, to just speak up and say that this isn't normal and that there are women in the field and they should have their place in the society. And in our organization, in our team, we have very, very active actors, Caroline and Marie. You can find Caroline in 2 common events. PyLadiesCon, it's an event online that will be held the 2nd and 3rd of December. You can also find her in Neurips, that will be held 6th and 7th, also free, but in Sorbonne University. And Marie, you can find her on Spotify, Deezer, and the Apple Store. She participated in the Adaptation podcast. It's very, very interesting, and you can hear her. We are also very active and very happy to announce our future special event. We are organizing visit of Institut Henri Poincaré. For those who don't know it yet, it's the first French museum that is dedicated to maths. It has been opened the 30th of September, sorry, and we are going to organize a guided tour and entry on the 10th of February. We will have 30 slots that are offered by the organization. So just look at our social media. We will have the event very, very soon. And you can find us on all social media, on X, Medium, LinkedIn. You can come to talk to us during the apéro slot, and you can also find us by email. Okay, so before today's agenda, I think Sharon will come to talk about Content Square that is hosting us together tonight. We are very, very pleased to be here, and about women in data and big data.
Great. Thank you. Okay, so let's begin. Who is Women in Big Data? So it's an organization a bit like Women in Machine Learning and Data Science that is very inclusive. So we want to put the spotlight on female practitioners and leaders and offer them tremendous effort, basically, by offering some mentorship program. We have a community of over 18,000 members, 40 chapters, 6 continents, and we have 2 kinds of reach, global reach and local reach. Globally, we provide some infrastructure, like I said, with the mentoring program, which is well-known. We are well-known for it. And locally, our chapter leader create events and try to also find some partnership like this one today. So we are really super happy to be organizing this one with Women in Machine Learning and Data Science. If you want to take action and get involved, so here is the global website where you can have a lot of free courses and the LinkedIn account to Women in Big Data Paris chapter. About Content Square. So I'm also very happy to be hosting this event as being a member of the Content Square family. For those who don't know Content Square, we are producing an analytics and UX platform for supporting our clients' decision-making. So the dashboard are provided with all kinds of capabilities, going through user journey, trying to provide also some session replays, and overall statistic. And we also provide some UX recommendation to our clients based on real-life data to improve the design of the website. So let's start. Okay. We're going to be, if it works. Okay, let's kickstart this meetup with a first talk about evaluation strategies when in a setting of partially labeled data or totally unlabeled data. So about us, I'm Sharone. No. Okay, I'm going to use the mouse. So I'm Sharone. I'm a machine learning engineer here at Content Square. I've been here for 2.5 years, and I'm mostly working on trying to predict intent.
Hello, everyone. I'm Daria. I'm a data scientist also here at Content Square, and I've been also here for about 2.5 years, and I've been mostly working on anomaly detection in time series data.
Great. So what's the agenda for today? First, we will start by stating the global picture and trying to provide basically a landscape of the evaluation methods we could use. Then we will have 3 case studies, emphasizing some evaluation methods that we would have presented before. The first case study, we're going to be purchase intent prediction. Second one is going to be unsupervised segment discovery. And third one is going to be anomaly detection for alerting. And then when we will finish, we will provide some key takeaways, trying to do basically a parallel between what's going on in academia and what's going on in the industry. So the global picture. Basically, the path to answering what evaluation method should you use can sometimes be straightforward if you have labels, and can sometimes be very complex. So the first question you should ask yourself is, do I have labels for the task at hand? If you do, then great. Most likely you're in a supervised setting approach. It's easy, you can evaluate your method, you can improve the machine learning model, it's great. But if you're not in this setting, and let's say you have no labels at all, or very few of them, you're most likely in a semi-supervised or unsupervised setting, if we put aside the reinforcement learning setting. So here, for the sake of simplicity, we will only break down our options to 4. So when you're in this setting of having no or few labels, the first option you could have is, okay, can I use public data set? Is there something in academia that could be useful for my use case? Is there some label data public that I can use? Second option you could have is okay, is it possible to design a proxy data set? Meaning, is it possible to find a data set where you have kind of pseudo labels? So it's not true labels, but it's something that is close to pseudo labels. And this will be exactly the focus of our first use case, purchase intent prediction. Third option, can I generate artificial data? Is there a way to have a session generator, for example, where you have artificial data that you can label because it's artificial and it answers some specific specificities? This will be the focus of our second use case, unsupervised segment discovery. And fourth option, can I get a manually labeled data set? Meaning, can I leverage some kind of domain knowledge, product knowledge in the company to label the data set? And this will be the fourth, the third use case, anomaly detection for alerting. Okay, going into the case studies. So as I said, I'm going to start with the first one, purchase intent prediction. And this is going to be referring to the question, can I design a proxy? So this project involves my fellow DS colleagues that are here, Mohamed, Felipe, and Miguel. So the main goal of this project is to answer who could have converted. And what we want to do here is detect within the non-converting users, the one that actually had the intention to convert, but didn't. And we want to do so based on behavioral aspects. So interaction with the product, add to cart event, clicks, hovers, all kind of behavioral that you can select. So in this picture here, what we want basically is that within the non-buyers, we identify the blue square, which is basically the missed purchase segment. For these two, we did some design choices. First, we focused on anonymous users, meaning we never take into account the history of a user. We focus on retail clients because we need to have the label of buyers and non-buyers. We do no difference between single item purchase and multi-item purchase. And finally, we do offline prediction. Once the session is done and you have all the information, then you can compute your prediction. In an ideal setting, if we had labels for purchase intent, what we would be able to do is to directly train a classifier, for example, binary classifier here, if we had labels for intent, in a totally supervised way to recognize intent. And this would help us twofold. It will help us to evaluate our model using some classification metric standards like precision, we call F1 score. And this could also help us for benchmarking and trying to compare different settings, different solutions in an unbiased way. But we're not in this setting. And the only labels we have today for purchase intent are only from the converting sessions. So schematically, what do we want? We want that on the left, you have actual conversion, positive meaning buyers, negative non-buyers. And on the right, you have predicted intent, positive intention to purchase, and negative didn't intend to purchase. What you want is that all the buyers should be predicted as having intent to purchase, because it's basically by definition, if they purchased, they had the intention to purchase at some point in the session. And for the non-buyers, what you want to do is to have some of them predicted as having intent to purchase, the one that you want to spot, and some of them being predicted as didn't have the intent to purchase. So what you want to do is basically take the whole population of the non-buyers and split them between the one that had intention to purchase and the one that didn't. So in order to do so, we need some kind of labels to evaluate that we're in this direction. So the first label that we have is that converting session had the intention to purchase. So all buyers, we already have the label. For the non-buyers, we don't have the labels. So the proxy dataset that we're creating here is that session that puts something in the cart and that purchase it in a later session, they probably had the intention to purchase. And this, how we designed it. We designed it first using a strict definition. What we use is that all the session where the items added to cart that you can identify with an identifier is actually purchased in a later session. And since, for example, if you're in a Decathlon website, and let's say you want to buy a pair of hiking shoes, and you come in the morning, you have some other stuff to do, and you come back at the end to buy it. When you added it to your cart, you most likely had the intention to purchase it. So this is some kind of pseudo labels that we have, but the issue here is that this identifier for items added to cart is not available for all Content Square clients. It's only available for Content Square clients that use the merchandising tool. So we needed to loosen a little bit this definition. So we created what we call the loose proxy set, where it's basically the same idea of add to cart event in one session that purchased in a later session, but we don't use anymore the identifier aspect of it, but we add another constraint, which is in the same day. So meaning if in the same day he added something in his cart and he did a purchase, then most likely he had the intention to purchase. So you loosen a constraint on one side and you add another constraint on the time frame on the other side. And great, this is available for all Content Square clients. We're happy. Schematically, how it will represent. So let's say we were to only use the label data, so only the buyers. If we only represent the behavior of the buyers at train time, what you want at test time is that the buyers of the test set is the closest to the buyers of the training set, and the non-buyers of the test set should be split it in two, one that are close to the buyers of the training set and one that are far from the buyers of the training set. And how you want to evaluate that it's exactly doing the way you want it to do, you will basically test it with the add to cart leading to conversion proxy dataset. And what you want is that this population of proxy dataset is basically in this middle population of session that didn't purchase, but most likely had the intention to purchase. So this will be basically what we call our missed purchase segment. Great, so we saw a first evaluation method. Now going into a second one, so the case study is going to be user segment discovery. And the question that is going to answer is, can I generate artificial data as an evaluation method for this case study? And this project involves my fellow colleagues here, Mouad, François, and Paul. So the main goal here is to answer the question, what are the typical paths people take? So there's a well-known tool at Content Square that is called journey analysis. So basically this tool, what it helps our clients is that it provides the granularity of all the journeys that their end clients are doing in the website. So for example, going from the home page to a search page to a product page and so on and so forth. But this is really too granular and it doesn't help us to regroup together some users, some session to create what we call personas. So the idea here is to create those personas based on the user page visit sequence, thanks to unsupervised learning, so really clustering. And the hypothetical outcome that you could have is basically, for example, those three personas. First one, early lever, homepage, product page, exit. Second one, heavy searcher, goes from home, search a lot, goes to multiple product pages, cart, and exit. And what we could call the golden converting journey is basically the journey that brings you to the conversion in a really flawless way. But wait, what are we really wanting to do we really want to evaluate something that is by definition unsupervised? So by definition, we don't have labels. Why do we want to do so? So there are some kind of metrics that are quantitative and that are already available in unsupervised learning. For example, if you're using hierarchical clustering, you can display a dendrogram and you can see how the split is done, basically. You can create some kind of distances, whether intercluster or intracluster. You can do some confusion metrics and trying already to understand how things work. But what you cannot do with it is to include business constraints. So let's say tomorrow, Content Square comes and say, okay, I think that those two journeys need to be in the same persona. You need to make this happen. And if you don't have a way to evaluate if the model is making it happen, then you don't answer their need, basically. And the second question also is that with only this quantitative metric, we cannot benchmark different settings, whether in terms of features, whether in terms of distances, or in terms of algorithm itself. So we ended up having an idea that we wanted to put, which is, if we have, for example, here 7 sessions that are represented by just letters, P for product page, S for search result, and H for homepage. Out of those 7 sessions, what we want to get is 3 patterns. We want to get the patterns of the one that mainly visited product pages in green, the one that mainly visited search results in red, and the one that looped between product pages and search results, which is in blue. So if we are able from those sessions to get these patterns, all good. So in order to do so, what we did is that we created toy scenarios where we have clear expectation on what the result of the clustering should be. So in order to do those scenarios, we needed to create artificial data. So we created 4 types of session generator. The first one is the session focused on one specific page. So for example, the sessions that only goes to product pages, browse products. Second kind of session generator, session having the given probability for each page group. A bit search, a bit product. Third kind of session generator, the sessions that are cyclings, always coming back to the same sequence. So for example, looping between search and product. And the third one, the sessions that contain a specific pattern. So really the sub-pattern of going from a search to product to a cart, for example. And what you want to end up having is this kind of table. You want to craft basically the scenarios in 2 categories. The one that are basic health check, and that should be mandatory to pass in order for the setting and the algo to be considered as an option. And the one that are a bit more complex, and that could potentially include some business constraint, and that could also show you what are the areas of improvement in your settings. So here, if we take those 3 settings, you see that there is no winning scenario per se, but you see that you're more likely to go with first and second settings than last settings. And I'm giving the floor to Daria for the third case study.
Thank you, Sharone. So I will present now our third and the final case study, which is about anomaly detection. And in that case study, we're kind of trying to answer the question, can I get a manually labeled data set for my problem? So in our platform, Content Square, we have one module which is called alerts. And the goal of this module is basically to alert clients when something on their platform happens and they need to fix it. So here we have an example of one metric, which is number of users with API errors. And we see here at one point, the number of users grew quite a lot. And at that point, we would like to send an alert to our clients and warn them, okay, maybe you should do something about it. And this is kind of a business problem that we're trying to solve here, but from a research point of view, this translates nicely to anomaly detection in time series. So when we were trying to tackle this problem using some research methods, well, we still first had to look at the data, of course. And one thing that we've noticed relatively easily in most of our metrics that we were dealing with is that they exhibit a very, very prominent seasonal pattern. And we were kind of happy with that because, okay, seasonality, this is something that we kind of know how to detect. We have different methods for that, and this is something we can handle. But there was also, on top of that pattern, a lot of variations in different metrics, and we need to kind of also draw some kind of confidence bound around those seasonality patterns to allow for some error. Otherwise, we would be just alerting on very small variations, and we don't want that. So our model finally consisted of those two main building blocks, which is seasonality detection and calculating confidence bounds around them. And here in this example, we can see that the blue line is our metric value. They have a daily seasonality, some variations, and then we are still able to infer in the red line the seasonality pattern, and we draw the confidence bound around that pattern. And then if the metric is really, really spiking and it surpasses the confidence bound, we raise an alert. And this sounds good. It looked good to us, and we were raising some alerts which seemed reasonable, but still we had to somehow evaluate our model in a more solid way, and we have to know that that in the future we will raise true alerts, and we will also not raise false alerts. This is something to be careful about. We don't want to spam our users. And well, the first thing that we were doing, of course, is well, we again looked at the data, looked at our algorithm results, and we looked at a lot of metrics, and the number of metrics grew as product wanted alerting on more metrics. And then at one point we were like, okay, this doesn't scale. We need some kind of a quantitative measure to evaluate our algorithms. And the first thing that came to our mind is something that is quite, again, common sense and something well established in all the research papers, which is looking at forecasting error, and which we can calculate easily by looking at the difference between the seasonality and the real metric values. And here we have one example. Our metric values go up to 800, and here our forecasting error is around 50, which again seemed reasonable, seems good, but how do we know that it's good? So then we tried to compare the error of a model which we thought that it's less smart than our seasonality model, which is a model that just predicts the last value. So this is something that we thought, okay, here the error should be worse. And I don't know, how do you think it is, but it turned out that the error of this dummy model was less. And we're like, okay, we don't want to use this evaluation method because it might prefer some models that we don't prefer. And we also noticed that this model actually raises some false alarms because it doesn't account for seasonality patterns, and it doesn't know when a metric rises, it will not know that it's actually a seasonality pattern. So yeah, we concluded that we really need to look at anomalies in terms of raised alerts. But annotating getting annotations at that level would be, well, it would be tricky. It would take a lot of time. And also from a business point of view, the feedback that we got from the product was, well, maybe we actually don't want to alert on those. Maybe something happened, but clients realize quickly what it is and they see it immediately. So we don't want to actually alert them on those. And then the final third thing that came to our mind, well, again, we looked at a bit more data, some real use cases that happened to clients, and one of those use cases was, for example, an iPhone launch that happened last year for one of our clients. And this is again the metrics counting API errors for users, and we saw that, okay, here something happened, but it didn't last just 5 minutes. It lasted actually, it was a couple of hours. And we saw that in other examples, again, when something happens, it's usually lasts more than 5 minutes. So we really need to think in terms of anomalous periods rather than just points. And that's why we decided, okay, we will then just try to get annotated periods of anomalous and non-anomalous behavior. And this is how we did it. Then, okay, it's relatively easily to know when a period is negative, meaning when nothing happens and when we shouldn't alert. And then we will say that, okay, our model is correct if in those periods in green, it doesn't raise any detections. And on the other hand, we also can annotate positive periods, meaning alarming periods, and we will say that our model is correct if it has at least one detection. And here we have an example where our model is working nicely. It's raising all the alerts that it's supposed to raise, and it's, on the other hand, not raising any alerts that it shouldn't on those calm green periods. And we were happy with that. And we were also happy because now we can have quantifiable results, and we have kind of a framework to evaluate our models. And something that we were also happy with, that this framework yielded kind of this kind of results where our last value model failed in terms of precision. Well, okay, for the recall, both models were raising anomalies where they should. This was good, but we saw that, as we saw in one of the previous examples, that last value model did raise some false alarm. So this evaluation method, we trusted it because it kind of also told us what we already knew, that our seasonality model is smarter than our last value model. So for now, we are happy with that procedure, and we're proceeding with that. And we hope that it will keep on like that. And we will still elaborate on that, but it's in the future. And yeah, I will now talk a bit about the key takeaways from all of those use cases that we presented. And I hope it was clear. So what we try to do through those use cases is draw some parallels between academia and industry. So we know that in academic setup, we usually have a relatively well-defined problem. For example, we can have some supervised problem with nice set of labels, and this will allow you to have a nice evaluation. And even if you don't have labels in a supervised setting, even if you're in an unsupervised setting, you can, with a clustering algorithm, you can still have some kind of a nice metrics that will like interclass distance that will help you evaluate your model. And then when you have your evaluation framework, you can peacefully focus on your machine learning model, and you can trust that your evaluation will tell you which model is best. But on the other hand, while you are dealing with a business problem, your main focus is really to even get to the point where you can have a framework where you will have an evaluation that you can trust. And here, this is what we try to do. We try to show some potential solutions to this problem by using proxy data set, by trying to leverage some business knowledge to annotate our data, and then hopefully you can have this framework that you can trust, and then you can also develop a model that will not only give you high scores or low scores, and you can have a model that will actually satisfy your business need and make your clients happy, which is in the end our goal. So yeah, that's the end of it. And now feel free to ask some questions.
Thank you very much, Sharone and Daria. It was very, very rich, and feel free to ask questions. There were many, many things that we learned today. It's always enriching to have the industry point of view and the research point of view. And coming from the industry, when it's not data, it's evaluating strategy. So I found myself there. So it's always the first one that's the hardest.
Thank you so much. I guess if I could just quickly follow up on the predictive model that you use for evaluation. So if I understood correctly, the observation was that the one step forecast model essentially followed your anomaly. So it wasn't a good metric to assess whether it was an anomaly or not. So would maybe and hence a more seasonal model was better was actually worse as a metric. But actually it's supposed to be better. So maybe would like a longer horizon forecast model, maybe, like a many time step forecast model, be a better inductive bias for your evaluation, essentially. So instead of predicting every next time step, maybe you stop and then you predict the next 100 or something.
Yes, a good point. Yeah, we tried. We did try that as well, and and indeed the error of then it grows larger, of course, if you're trying to predict. For example, so here we're talking 5-minute interval. So if we try to predict it from last hour, it was a bit noisier, but still, in our opinion, it was still quite good, because the seasonality sometimes, it's sometimes also you have a strong seasonality, sometimes you don't. So again, on some metrics it was kind of a better measure, on some not. So still we weren't happy quite even with that. And then, and also from a business point of view, for some metrics you need to you don't actually care that much for much future predictions. So you don't want to actually look much in advance, and so you can just actually use the last value. So it kind of, this metric also, yeah, we basically weren't happy with that evaluation either.
Right, thanks.
Yeah, thanks for the talk. I also have a question on anomaly detection. I'm curious how you annotated things. Did you have internal data scientists annotating, and did you actually have agreement between annotators?
Yeah, that's just basically long discussions among ourselves and with the product people, and that's basically the whole process. And this is something that we're still working on to improve, to automatize, and maybe to then outsource the annotations to our annotating team that we have here in Contextware, because for now it's really only us trying to agree with the product, and then maybe if we realize that we have some like rules that could be applicable, that we could explain to other people so that they can also annotate, then we might move forward with that. But for now, it's really just us talking to products. And yeah.
So did you manage to actually find rules that work for
not
all
yet,
metrics?
not yet, because it's a really, and now it's a very context dependent, and sometimes you need to know also from the client side what's happening. You need to ask them, okay, was there something also that you did that caused those spike on your platform? So it's not easy.
So are you considering using proxy labels?
Oh, yeah, we considered, but I don't know. We then kind of have this additional step where we have to evaluate that the proxy is actually a good thing. So we found this process to be more complicated than actually designing the annotations. So yeah, but we're looking in different directions. Yes.
Okay, thank you.
Thank you for the presentation. It was very interesting. So can you use this GAN for generating, because we can reduce the labor, like few examples with SMEs, with the help of SMEs, we can label, and after that we can use GAN for synthetic data, for generating synthetic data, right? So that we can increase the amount, the volume of the data, and maybe we will get a better models from that one.
You mean also for the anomalies in time series?
Yes.
To as like GAN
Like proxy data, when we are the main problem is the labeling and everything, it's very time consuming, so we can concentrate initially on the very good quality data for with the help of SMEs and proper evaluators we can generate. After that, with the same distribution, based on the same distribution, we can multiply that data set using GAN. GAN means automatic, because I'm working for an aviation domain, so mostly we were also having this kind of issues like lack of data, otherwise the very poor quality data. So we will correct our data with the help of SMEs, then we are using the GAN.
Okay. And as an input, you would give it the time series, and
Yes.
you feel like okay, if
Yes.
it would be able to generate good enough.
Yes, because in the time series, some places we were missing. Those things we can use with the can we? That's maybe.
It could be. It could be maybe a faster. Okay, we could try this. We could verify if the output of the GAN kind of agrees with our vision of the anomaly, and then once we trust it, we could maybe ask it just to extend further. Could be an option. Yes. Yeah.
Maybe because that's one proof, because we tried in our system and it's working well. Not very, we can't say every always been synthetic. It's always a synthetic only, but something we will get it without much effort.
Yeah. Something to try. Yes.
Yeah. Thank you so much.
But if I were to answer for the other use case of unsupervised segment discovery, even though we generate artificial toy scenario, if we were to really generate artificial sessions, would have been difficult, because it's really dependent on human interaction and human behavior with the platform, with the website itself. And this is, and in terms of features, since you can have like 60 features sometimes to represent the data in terms of clicks, hovers, etc., it's a bit more complicated to go with GAN related options.
Yeah, yes, I know. Thank you.
Thank you. I think we can have a round of applause. So now we're going to have the research point of view. So there's going to be Sophie and Shikha from InstaDeep, and the floor is yours.
Or I take this one, other one. Yeah, okay. All right. Anyway, wow, so cool to be on this side of the room after so many years following the meetup. So thanks for the team for the opportunity to present. It's a pleasure to be here tonight. So yeah, we're gonna talk with Shikha about the InstaDeep and actually Compass, some of our combinatorial optimization, reinforcement learning. So it's a paper that we submitted and that was accepted at NeurIPS 2023. So actually, we're super happy to have Shikha present it in the US in a couple of weeks. Before that, just a few words about InstaDeep from the research prism, because I don't know if you guys know us, who we are, or what we do. So maybe that's the first question, like who in this room knows or has heard of InstaDeep before tonight? Okay, so we're like 15, 20% of the room. Yeah, so InstaDeep is now a 10-year-old company, right? So we're about 350 people. We're present in 10 offices across the world. So the Paris office, where I'm based, is about 120 people. And then we're also present in London, where Shikha is based, Berlin, Cape Town, Boston, San Francisco, and a few others. Among these 350 people, a thing to note, since this is the research talk, is that over 10% of our workforce are full-time researchers, so mainly focused in publishing in academic journals and attending academic conferences. And this is actually at the heart of InstaDeep, to be research-driven. And these two, we're focused on two research verticals, which are one, reinforcement learning, generally, and the other one is bio-AI, so basically the use of deep learning, whether it be language models, graph neural networks, diffusion models, whatever in the context of bio AI, so for biology. And again, as far as the research is concerned, like, first of all, if we want to handle all the pipeline of a data project, it starts with us with the fundamental research. So we are very happy to be partnering with top universities in the world. So UCL, Oxford, Cambridge in the UK, École Polytechnique, Sorbonne in Paris, MIT, for example, in the States. But we're also super lucky to be working with the, frontier AI companies in the world. So we've published with Google DeepMind a few years ago, and we're still collaborating with them. And we are also one of the 2 NVIDIA elite partners in the European region. First of all, because we trained large foundational models, for example, in the genomics field on supercomputers based in the UK. And we also have our own cluster in the UK, composed of a few hundreds of, DGX GPUs, which is about also to scale next year. And then we want to apply this research, right, to a lot of companies. So I would say, if I cited 2 companies, one would be Deutsche Bahn, which is the German SNCF. And we tackle multi-agent reinforcement learning problems with them for automatic train scheduling and delay management. And the other big collaboration is with BioNTech, for example, on designs of vaccines. So think COVID vaccines, think cancer vaccines. And this led actually to our recent acquisition by BioNTech in August for an amount of $700 million. And finally, again, research-driven before diving into Compass. We're super thrilled this year to have 13 publications accepted at NeurIPS, the US one, not the Paris one, with research tracks ranging from, in reinforcement learning, we deal with combinatorial optimization, offline reinforcement learning, multi-agent reinforcement learning. And as far as bio AI is concerned, graph neural networks, diffusion models, protein language models, but we also deal with RNA or genomics language models. So I hope that this gives you a bit of an overview of our research teams, right? So over 40 people, and I'll hand it over to Shikha to go over Compass.
Perfect. Thank you so much, Sophie. All right. So my name is Shikha, and I'll be talking about our work, which is combinatorial optimization with policy adaptation using latent space search. So it's a bit of a mouthful of a title. So we call it Compass. And it tackles the field of combinatorial optimization. So let's start here. Let's talk about what this field is. So this field of CO, it spans vital real-world industrial domains like transportation and logistics. And the aim in this field is to solve combinatorial problems. And so a combinatorial problem can be defined as a problem which has a finite set of possible solutions. And what we would like to do is find the optimal solution in that set of solutions. And usually we do this by optimizing some objective function. So to kind of give you an example, on the screen here, you can see on the left, we have traveling salesman problem, TSP. And so this is the problem where you have a bunch of different cities and you want to find the shortest route between the cities. So the set of possible solutions would be all the different routes you can take, and the optimal solution is the shortest route. The other 2 problems are CVRP in the middle, capacitated vehicle routing problem, and JSSP on the right, which is the job shop scheduling problem. I'm presenting these 3 problems because these are the ones we tackle in our work, but our research can be applied to all different types of CO problems. Okay, so now let's move on to the challenge with combinatorial optimization. And this is when we increase the problem size, the set of possible solutions grows exponentially. So for example, the problem size in TSP would be 10 cities. And if we increase it to 100 cities, the set of possible solutions grows dramatically. And to kind of give you an indication of how dramatic this is, let's say I'm a TSP machine and I can compute 100 routes per second. So if you give me a problem with 10 cities, easy, I can do it in under half a day. I can give you all the possible routes. Now you're saying double it, 20 cities, you're going to have to wait a bit because it's going to take me over 700 million years to compute all the possible routes. So yeah, to brute force these kind of problems is just not an option. So what researchers have done in the past is that we develop kind of heuristics. These are like smart, hard-coded strategies, but they're hard-coded, so they give like suboptimal solutions. And this is where reinforcement learning comes into play. So reinforcement learning has been applied to a range of CO problems, and they provide near optimal solutions. So before I talk more about that, let's have a bit of a refresh on what reinforcement learning is. So it's a learning method used to train any decision-making function, for example, like a neural network. And it's very much inspired by behavioral psychology and kind of like how us humans learn, like through trial and error. And so in RL, we have an agent, that's our decision-making function, it's our policy, and it interacts with the environment by performing actions. And by performing an action, you change the state of the environment. So as it performs an action, it gets a new state from the environment, it goes to the agent, and it also gets a reward for performing that action. So the goal of our agent is to learn a strategy, a policy that will maximize its rewards. And so it does this by interacting with the environment, performing different types of actions, and then adjusting its behavior based on the rewards that it receives. So in very simple terms, we train a policy by giving positive rewards for good actions it takes and negative rewards for like undesirable actions. Okay, so now let's move to what the goal is in our field. And so in the field of CO, the goal is to optimally solve NP-hard combinatorial problems under a budget constraint. And a budget is basically the number of attempts that our method can propose to solve a problem instance. So it's basically the number of solutions that it can give. And reinforcement learning is a very promising avenue to tackle CO problems because it trains policies that can construct a solution for a given problem. A lot of methods, they do this in kind of like a one-shot attempt. So they construct a solution, but it's so hard to get the optimal solution in just one go that competitive methods, what they do, they blend a pre-trained policy that gives you your solution, your one-shot attempt, and then you have additional search procedures that can kind of improve over the solution. However, prior works, the search procedures that they have is like, they're either very simple, so it's just stochastic sampling or beam search or Monte Carlo tree search, or they're computationally expensive. And this is kind of like retraining your network weights during your search procedure. And since you have to retrain network weights, it becomes very computationally expensive. Another limitation is that these methods, they don't significantly improve over the search budget. So what you would want from a method is that given your search budget, it continually improves upon the solution that it provides. And so eventually you would hope to reach the optimal solution. However, many methods don't do that. And they also have poor generalization. And so this is where our method comes in. We try to overcome some of these limitations, and we propose a structured latent space of diverse policies that you can search during inference to find the best, the most performant policy for your given problem. And we will show with our results that we achieve state-of-the-art results both in distribution tasks, and we can also generalize to out-of-distribution tasks. And so our method kind of improves upon the conventional paradigm of just stochastically sampling policies. And what we do instead is that we search our space of policies. All right, so this brings me to our method Compass. And the idea behind Compass is that you want to train an infinitely large set of diverse policies, but by only conditioning on a single set of policy parameters. So what this basically means is that you only have one network, you only have one set of policy parameters, but because you condition it, you can have an infinitely large set of parameters, and we condition it upon a continuous latent space. This may not make total sense now, but I promise once I get a bit more deeper into the method, it'll make more sense. So our method is split into training and inference. During training, you want to, we use reinforcement learning with a competitive training objective to have a continuous space of diverse policies. And then during inference, we utilize this diversity within the latent space to apply a principled search procedure that we can search our latent space, find the most performant policy for our given problem instance. So let's take a look at the training in a bit more detail. So during our training procedure, the very first step is to sample, let's say, n latent vectors from our policy latent space. Once you have these n vectors, what we want to do is we want to condition them on our single network policy. And the way we do that is that, let's say you have your network, the input to your network is going to be the problem instance, and then the second part is going to be the latent vector. And as a result, if you have n latent vectors, you get n conditioned policies, and the conditioned policies, they tend to behave differently, and so you result in n different solutions for your given problem instance. Now, the third step is that when you have your n solutions, we now want to evaluate the solutions. And so, for example, let's say we have the traveling salesman problem, TSP. The way we evaluate it is that we find the tour length of the route you took, since we want to rank it by the shortest path. And so, yeah, once you have evaluated your solutions, you can rank the latent vectors based on the quality of the solution. And once you have this ranking, we can now move to the fourth and final step, which is to train our policy. And the way we do that is that we take the best latent vector, so the one that produced the best quality solution, and we use that to update the weights of our network. And we only use the best latent vector to update the weights because this creates kind of an implicit specialization within our latent space. So we don't use any explicit term in our objective function to create this diversity. It's just by training the best latent vector on the given problem, we can get this implicit specialization. And when we do this kind of training, we can see that the different areas of our latent space, they specialize to different areas in our problem distribution. So you have different policies that are specialized to different instances in your problem distribution. And then we just repeat this process until convergence. Now let's take a look at the inference. So the first step is the same during as was in training, that you sample a batch of latent vectors from your policy space. Once you have that, you want to again condition your policy on these latent vectors given your problem instance, and then you get n solutions. And once you have that, you want to again evaluate the solutions, and then you want to use the quality of each solution to update the distribution that you use to sample your latent vectors. Because what you want to do is that you want to update the distribution such that when you sample the latent vectors, you kind of maximize the likelihood of sampling those vectors that led to the best solution. So here, as you can see on the image over here, that you move towards the high-performing regions because you want to move towards the high-performing policies in your latent space. And then you just repeat this process for your evaluation budget. All right, so now we're going to move to the fun part, which is the results. And so we have, so we'll start with the combinatorial problems that we tackle, and these should look a bit familiar. These are two routing problems. We've got the traveling salesman problem, the capacitated vehicle routing problem, and we also have a packing problem, which is the job shop scheduling problem. We also compare our method Compass to prior RL state-of-the-art baselines. And we have 3 of those. We have one, which is POMO. It's a very foundation for a lot of RL CO work. It is a single agent, one-shot architecture. We have EAS. This is also single agent. And what this method does is that during the search procedure, it fine-tunes its policy, which means it updates the network weights according to each test instance. So this is our computationally expensive baseline, but it performs really well. And then third one is POPI. It is a fixed population of policies that are diverse, and then during inference, you just stochastically sample these fixed set of policies. And a little fun note, POPI is actually also an InstaDeep research project. It was the predecessor for Compass. All right, so our evaluation, it consists of 29 tasks spanning over 6 categories. And these categories can be seen on the vertices of the radar plot. So these include both in-distribution tasks and also out-of-distribution tasks. Those are the larger instances, large shift, small shift, and medium shift instances. We also have few-shot evaluation tasks, and this is basically when your search budget is significantly smaller. So this is when you want really only a few attempts, you want your answer really quickly. And so as you can see on our radar plot, this plot, it highlights the strengths and weaknesses of all the approaches on the different categories. And as you can see in red, our method Compass, it outperforms all of the prior baselines on all of the 6 categories, showing its versatility for all different types of tasks. And in particular, you can see for all the generalization tasks, it does outperform all baselines. And this is kind of like very impressive to show such strong generalization capacity. And I would like to spend a little bit more time on that. So the way that we measure generalization is that we create out of distribution instances. And so the way to do that is that we take a test set in distribution instance. And so on the screen here, you can see as random uniform, I've taken a TSP instance. And this is usually what's in distribution. It's in our test set. And what we do is that we apply mutation operators to it. For example, here you can see what happens when you apply the explosion and implosion mutation operator. And what this basically does, it kind of shifts the underlying distribution with which the cities are scattered. And each mutation operator has a mutation power associated with it. And this power allows us to, well, as you increase the power, you can have more and more out of distribution instances. And this just allows us to study the method's performance as we increase this going more out of distribution. And so on the bottom plot, you can see the comparison of the baselines to Compass based on the performance ratio for both TSP and CVRP. So here in red, we have Compass. It's at 0, showing like what the performance of that is. And then here you have the baselines kind of comparing the performance to Compass. And you can see that the performance of all the baselines is worse than Compass. So Compass tends to perform better for all the mutation powers, and in particular for mutation powers that are very high. And so basically with this, we want to show that Compass is able to generalize better because it can adapt its policy during inference time. So even for instances that it hasn't seen during training, because it has such a diverse set of policies, it's able to adapt its policy and still perform near optimal for out of distribution instances. And finally, I would like to spend a little bit time on discussing the search procedure that we have during inference. So we have, there are all the different methods, Compass and the baselines, they have different ways of performing during the search procedure. So Compass, it searches its latent space to find the most performant policy. POPI samples its fixed set of policies in a stochastic way. POMO has one policy which it samples stochastically, and EAS fine-tunes its policy parameters. And here on the top plot, if you look at the left one, you can see the evolution of the different methods as you increase the search budget. So this is for TSP, and on the y-axis, we have the average tour length. And for TSP, we want the shortest tour length. So you can see that Compass in red performs the best out of all of the methods. And in particular, it has the most significant improvement throughout the procedure. And this is thanks to its search during the latent space. And here we use CMAES search. So if you look at the bottom plot, you can kind of see the trajectory of CMAES, and you can see how it starts at not the darkest red region, but it moves towards the really dark red region, and that kind of denotes the high performing region. So you can see the latent, so this is an image of the latent space, and you can see it's very well structured. You have low performing regions, you have high performing regions. This is for a given instance, and you can see that our search procedure also works to find the high performing region. All right, just to end, I just want to give a conclusion on Compass. So Compass offers a framework for training and effectively searching a set of specialized policies during inference. We set a new benchmark on RL-based CO methods. We surpassed all prior baselines on 6 categories spanning 29 tasks. And in particular, we show really good generalization capacity. Thank you all very much for listening.
And thank you for sharing. I think it was very interesting, and the explosion was in my head. Do we have any questions in the room?
Hi, thank you for the interesting talk. I think I will need some time to process everything.
Sorry about that.
But I had a small question. So you said that you have a diversity of policies due to the sampling in the latent space. Mm-hmm. But is the diversity just due to the randomness of the latent vectors, or do you impose it? Do you have some repulsivity between latent vectors or something like that?
Yeah, no, that's a really good question. So I think the diversity is a little bit unintuitive, and it only comes from training the best latent vector. If I go back to here, it only comes from training the best latent vector, like updating the weights. Because if you only update the best latent vector, you're kind of only training it for that particular problem instance. So you can imagine when you have, let's say, a batch of problem instances, and you have, you know, a bunch of different latent vectors, usually they will get trained on different problem instances. And since they're getting trained on different instances, that's how the diversity is created, if that makes sense. But when we sample here, we just sample randomly. So it's kind of very convenient because you can use it for any type of problem without understanding how you want to implement diversity, because we do it in such an implicit way. So it's kind of like an off-the-shelf method that you can use.
Okay, I got it better. Thank you.
Do we have other questions, or do you need to process it? Okay.
Thank you for the talk. Do you have the room for improvement? What kind of problems on which it doesn't work yet, or do you have an example to give?
No, not this question. There's definitely room for improvement, and I would go to when I'm talking about the latent space, we don't have a really good understanding of what exactly, what is the diversity. For example, we think that policies are different because they have different strategies, But our method at the moment, what we do over here, we sample, for example, 128 latent vectors. So it's 128, for example, conditioned policies that you're rolling out, and we only train one. And this is a massive, okay, not massive, but like a pretty big like waste of the rollouts and of the compute that you're using. And so if there was a way beforehand to kind of know which latent vector would be good for the problem instance, it would help us, for example, really speed up training, but it would also help us during inference, that we could just get the best performant policy in only a few attempts. But it's really hard to know how the policies specialize because it's so implicit, which is the good side because it's easy to do, but it's also the bad side that it's a bit hard to like understand and anticipate, if that makes sense.
Yeah, thank you.
Thank you. I wonder if the fact that you use this latent space may allow you to use that kind of algorithm, but in a like a genetic algorithm. Like you would combine two vectors to do like childs, like it's done in the genetic algorithm.
Yeah, I think that's a very good point, because as we've seen in the latent space is that latent vectors that are close to each other, they tend to have similar performance on a problem instance. So I think using the information of your neighboring latent vectors definitely, yeah, could help.
Okay, thank you. If you have any other questions, do not hesitate. But do not hesitate, I was saying for the apéro time. Thank you, Sophie. Thank you, Shikha. And now to our last talk. Thank you, Caroline.
Okay. This will be a lighter talk, I hope. So I'm very happy to be here today to talk about this subject. Generally, when I talk about age, I talk about my grandpa, but today I won't. This will be more personal. So for the first 15 years of my career, people kept telling me that I was young. Once an HR told me that I could not be manager, I was too young. I was not exactly too young, because at the same age, my boss was promoted director. But well, she thought I was too young for the job. But 2 years ago, I was having a discussion with a woman advocating for more women in tech. And she told me, you know, it's good that you look young, because in tech, after 35, you're over. I didn't see that one coming. So I start to pay more attention about age and ageism. And you know, when you become aware of something, you start to spot it everywhere. But well, before I tell you more about this age subject, maybe I tell you more about myself and how I switched from never old enough to never young enough. So I grew up in Martinique, in the French West Indies. I moved to Paris to study, and I didn't have a clear career goal at that time. But I wanted to see the world. I had my first experience in Argentina, my first expat experience in Argentina, and I really wanted to see more of that. So I did a lot of travel, first as an auditor, and then I was working in the telecom industry when I went the first time to Nigeria, and I discovered that you could image computers to do investigations. And I got quite fascinated about this job. And I turned out to be quite good at seeing things others didn't, that mean fraud. And I later became the first corporate investigator for Europe, Middle East, and Africa of the company. In 2015, I moved to the DRC to work for a mining operation. This was a completely new world for me, but this was definitely a great learning and quite life-changing experience. 2 years later, I came back to Paris, this time to work in forensic consulting. And it turned out that finding my place there was way more difficult than in the middle of nowhere in Africa. So at some point, going to the office became quite unhealthy for me. So I was kind of in the middle of a crisis. Time will tell if this was my middle-age crisis. But and then came the pandemic, so another crisis on my crisis. So I was not so happy. But one morning during the lockdown, I had this thought: to be happy, you need to do the things that you liked when you were a kid. So when I was a kid in Martinique, in my world, the coolest thing in the world was to go to the math classes. So I did that. I started to follow math classes on MIT OpenCourseWare. And from there, I decided to upskill in data science, and to start my own business. So on this online journey, I was kind of living like an hermit. So I wanted to meet new people, and this is how I heard about Data for Good. And I found this very welcoming community. No one asked me about my age or my background, and that felt really good. And earlier this year, when I heard that Data for Good was launching this project to write a white paper on the challenges of generative AI, I decided to join the team. And for me, it was the perfect opportunity to explore more about this age bias. So this project is broader than just bias and discrimination. It involves, we also explore misinformation, copyright, and environmental impact. I invite you to read it if you're a French speaker. It was a collaborative writing, so more than 40 people participated in the project. All were volunteers. So if we try to define ageism are basically stereotypes and discrimination against both young and old people, and based on their age or their presumed age. So these are a list of stereotypes, both negative and positive, for younger people and older people. As you can see, the list is much longer for older people. But if we focus more on tech, well, you will see that a common stereotype is that young people are tech savvy, while older people are generally not technologically competent. So if we now try to understand where ageism can emerge in AI and in tech in general, we can look at 5 dimensions. This is proposed by Justyna Stipinska. So the first dimension refers to the technical level, and this is probably the one that you're most familiar with. This is based, this refers to generally the fact that data sets do not include samples of for people over a certain age. Then you have the second dimension, which is the personal actor level. And this refers to some stereotypes or let's say ideologies that are spread by actors working in the tech industry. So for example, you have this imaginary of teenagers starting to revolutionize the world in their garage, and this creates this myth that innovation can only be done by very young people. You also have this famous speech from Mark Zuckerberg, who said that young people are just smarter and tech companies should not hire people over 30. So this leads to quite homogeneous recruitment in the industry. And about this, I thought it was interesting to show you this survey that was conducted in the UK. And as you can see, in IT and tech, this is the sector where people get older, the youngest. So as early as 29-year-old people start experiencing ageism. And this is 12 years before the average. Then you have this third dimension that is referring to the discourse level. So this is related to the fact that in the AI research for ethics, or in events like this one, generally bias and discrimination is quite focused on gender or ethnicity, and generally not so much on age. And as a consequence of that, there is a lack of awareness about ageism. And the next level is the group level, and this refers to automatic decision-making algorithm that can discriminate massively some age groups, like in hiring, for example, or in some surveillance systems. And the last level is the user level, and this refers to these preconceived ideas that older people will not use some products, and this is a priori conception. And sorry, I don't have my notes. so about this user actually level, this is quite yes, this can also be seen in the health sector, and actually in the health sector is the one where older people could benefit most of products, but sometimes they are excluded from the very first conception and the design of those products. So about this user, I have this funny story that I had this last summer with my mom. She was very fan of my avatar, and she asked me how she could get her own. So we looked at the options to get her avatar, and color skin was okay, dress was okay. But when we looked at the wrinkles, this is where it was very difficult to find something. So I don't know if you can spot the wrinkles, but for me, I really had to work to look very, very carefully. And she really felt excluded at the beginning, but well, I told her these were wrinkles with Botox, so she accepted this much younger version of herself. So I was very curious to know how stereotypes are present in generative AI, and how senior or retired or older people were represented. So for this white paper, I took a list of adjectives that were in among those stereotypes and their antonym, and I decided to use the DALL-E API to generate images based on those adjectives, and I generated 3 types of prompts. So the first one was age neutral, a person, and then a senior person, and then a retired person. So these are the images for the first prompt for person. And it's always a subjective exercise to assess people's age based on an image. But generally, older people were not present in the image that were generated, and the only, let's say, noticeable difference was when I generated the images for inactive and active people. So where you could see a lot of gray hair and wrinkles were generally for the inactive person versus active person. There are other types of stereotypes in this, of shocking stereotypes in these images that are not related to age, but I will probably let you with the white paper, or we can discuss it in the apéro after. So yeah, these are the few older people that I spotted in those 600 images. And these are the images for the retired people. And I don't see if this is visible for you, but what struck me at first sight was the lack of diversity in terms of ethnicity. So if we now look at the figures, well, by default, there were not that many women, less than 13%. But for the retired person, it was quite impressive that you had less than 2% of women. And I compared this figure to the real figures. So actually in France, the older you get, the more women. On the left side, you can see the real figures from INSEE, the National Statistic Institute. And actually there are more women that are retired in France than men. Now these are the analysis for ethnicity, and by default, there were quite many more European people, but the older you get, the less diversity again. And as you can see, there were only Caucasian people for senior and retired women. So I could talk for ages about this subject, but well, I guess you all want to have the apéro. So if you want to continue the conversation, we can connect on LinkedIn, or you can join us at Days Are for Good and participate to other projects with us.
Thank you so much, Caroline. We really need people like you to speak so that we can spot this now everywhere. So I'm really sorry we don't have time, but you can talk to Caroline during the pizza time. Now I will invite the other Caroline to come. Some of you have given their names for a lottery to win mathematics book. Okay, but if there's one really hard question
for this
Caroline, maybe during the time that we set up the lottery, or sharing of point of view.
You feel old, right?
Well, there was no personal attack in my talk. I guess the population is very young.
So some of you answered when you entered the room. We have 2 books about map making and mathematics. And so now I'm going to press the button to see who won. It's randomly selected, of course, and unbiased. So the first winner about la créativité en mathématiques is... C'est plouf plouf. Amira K. Woo, woo, woo. That's for you. And the second one, which is entitled Le rêve de la carte parfaite, is going to go to Sandrine H. So now you can all get fed, hydrated, and I would like one volunteer to take a picture with all the speakers from tonight's session. And thank you for being so numerous to show up. We have lots of new faces, and diversity in all its splendor is really improving. So thank you. Thank you for being so loyal. Et merci Julien pour la technique. Woo!